Welcome to Mathematical Physics 1. Today, we are going to explore a fascinating and highly practical mathematical tool known as the method of undetermined coefficients. If you have ever wondered how physicists predict the exact way a building will shake during an earthquake, or how an electrical circuit responds to an alternating current, you are in the right place. Let us dive in and demystify this concept together. Before we look at any equations, let us build our intuition. Imagine you are a detective trying to figure out what kind of vehicle left tracks in the mud. Thin grooves suggest a bicycle, while massive treads suggest a tractor. You know the general family of the vehicle just by looking at the shape of the tracks. In mathematics, when we apply an external force to a physical system, the system's response usually looks a lot like that force. If you push a swing with a rhythmic, wave-like motion, the swing will eventually move in that exact same wave-like pattern. The method of undetermined coefficients is exactly this detective work applied to differential equations. Now that we understand the intuitive detective work, let us look at the formal definition. We use this method to find a particular solution, often called the particular integral, to a non-homogeneous linear differential equation. But what does non-homogeneous mean? It simply means our equation has a non-zero function on the right side of the equal sign, which we usually call g of x. For this specific method to work, the left side of our differential equation must have constant coefficients. This means the properties of our system, like mass or resistance, do not change over time. Building on that definition, how exactly do we apply this method? The magic happens because the driving function, g of x, belongs to a very specific family of functions. We are talking about polynomials, exponentials, sines, cosines, or simple combinations of these. Instead of performing complex and tedious integrations, we take a shortcut. We simply assume that our particular solution is a general combination of the driving function and its derivatives. We write down this assumed form using unknown constants, which are our undetermined coefficients. Finally, we substitute this guess back into the original equation to algebraically solve for those exact numbers. You might be wondering, why does this specific method matter so much in mathematical physics and engineering? The truth is, in the real world, physical systems are rarely left alone in a vacuum. They are constantly being driven by external forces. Think of a car driving over a bumpy road, or an alternating current voltage applied to a circuit. The differential equation models the system itself, and that non-homogeneous part represents the external driving force. This method allows physicists and engineers to quickly and accurately predict the steady-state response of the system to that exact force, saving us from error-prone integration. Let us translate these real-world concepts into mathematical representation. On screen is the general non-homogeneous linear differential equation. The symbols A, B, and C represent constant real numbers. Physically, these are the fixed properties of our system, like mass, friction, or electrical resistance. The variable y is the unknown function we want to find, representing the system's position or state. The function g of x on the right side is the external driving force. If g of x increases in magnitude, it means the system is being pushed harder. Consequently, the resulting particular solution will also scale up proportionally to match that increased force. Now that we have our general equation, let us look at our first specific guessing rule. This formula shows the core logic of our strategy for exponential forces. If the external force, g of x, is an exponential function with some constant multiplier c and an exponent rate k, we guess that our particular solution will also be an exponential function with that exact same rate k. The symbol a represents the undetermined coefficient that we need to find. We do not know what a is yet, but we know it must exist to balance the equation. If the input rate k changes, our guess must also change to match that exact new rate perfectly. Let us put this exponential guessing rule into practice with a concrete example. We are given a differential equation where the system is driven by an exponentially growing force, 4e to the power of 3x. Because the right side is exponential, we guess our solution is a times e to the power of 3x. We then find the first and second derivatives of our guess using the chain rule, bringing down factors of 3. Next, we substitute these derivatives back into the original left side of the equation. By factoring out the exponential term, the algebra simplifies beautifully. The a terms partially cancel out, leaving us with 2a equals 4, which means a equals 2. Physically, this tells us the system's forced response exactly follows the path 2e to the power of 3x. Having successfully solved an exponential problem, we must now look at oscillating forces, which require a slightly different approach. When our driving force is a sine or cosine function, we must be very careful. The derivative of sine is cosine, and the derivative of cosine is negative sine. Because they cycle into each other, our guess must include both sine and cosine terms to capture all possible terms that might appear. We guess a times cosine of x plus b times sine of x. Here, a and b are our two undetermined coefficients. If we only guessed sine, we would be missing pieces when we take the derivatives, and the equation would not balance. Let us see this trigonometric guess in action with a classic physics problem, a simple harmonic oscillator being pushed by a wave-like force. Our equation equals 3 sine of x. Following our rule, we guess a combination of sine and cosine. We take the second derivative, which simply flips the signs. We skip the first derivative here because our original equation does not have a y prime term. We substitute our guess and its second derivative back into the equation. The crucial step is grouping all the cosine terms together and all the sine terms together. By comparing the left and right sides, we see the cosine coefficient a must be 0, and the sine coefficient 3b must equal 3, so b is 1. Physically, the system oscillates in perfect sync with the driving force. Now that we have worked through the math, let us zoom out and look at the overall strategy. What you are seeing here is a visual flowchart summarizing the decision-making process for this method. At the very top, our first step is always to identify the driving force, g of x. From there, the path splits based on the shape of that force. If it is a polynomial, we guess a polynomial. If it is an exponential, as we saw in our first example, we guess an exponential. And if it is a sine or cosine, like our second example, we guess a combination of both. All these paths converge at the final step, substituting the guess into the differential equation to solve for the exact constants. We have covered a lot of ground today, so let us review the key takeaways. The method of undetermined coefficients is a powerful shortcut for solving non-homogeneous differential equations. Instead of integrating, we make an educated guess about the shape of the system's response based entirely on the external driving force. We set up a template, plug it in, and use basic algebra to find the exact values. While it only works for specific functions like exponentials, polynomials, and sinusoids, these are exactly the most common forces you will encounter in physics and engineering. You now have a fantastic new tool in your mathematical toolkit.